So Lux just blew that away. Lux is in complete disagreement with Dama. So, yeah, it's depressing, but you know, one of the few areas where we can think to look for new physics. What I mean by depressing is there's nothing's been seen. And just like the Higgs, only the Higgs came out. That was depressing. Dark matter, nothing's come out. It's kind of depressing.
Still stop.
It's still not. So, yeah, there's very nice exclusion plots I don't have in the the one thing I will say though is if dark matter is heavy, and you look at then treating dark matter with some heavy effective field theory, heavy state effective field theory, it is true today that the strange charm followed by the up and down quark matrix elements provide the largest uncertainty in those searches. So there's still room to try to improve our understanding of those matrix elements.
I have a question. So when people talk about intrinsic exchange in the proton, so in your calculation can refer to the exchange content in the proton. And this content depends on scale. And then your scalar current depends on scale too. So your calculation should depend on some scale.
But if I multiply it by the strange quark mass, you remove all that scale dependence. So if you ask the question, what is MS S bar S? That is a scale scheme independent question. But if you ask what is the S bar gamma mu S, then you have to, yeah, so if you want to know S bar gamma 5S and these other matrix elements, then you have to define a regularization scheme of scale. So that's why this one is easy, because the scale dependence cancels.
And usually how this scale come into the lattice calculation?
So approximately the lattice spacing is the inverse scale. So then you can smooth the gauge fields to run that down to a lower scale. And you can perform calculations with finer lattice spacing to look at higher scale. I seem to have lost my microphone. You can look, there's techniques you can use to run the scale in the lattice calculations. You can come up with some non-perturbative scale dependence, and then run that to a high energy scale where you believe perturbation theory, and then match on the MS bar.
So there's a nature to the
Yeah. There's a very technical work to do the lattice renormalization. So you need people who can do the continuum renormalization and the lattice renormalization and match them together.
So I see no further. Oh, there's a one.
You run the hollow state as three spinner part, right? Is that based on some model or some assumption?
Is it a model assumption? Is that the question?
Yeah.
So, the choice. So this operator here. This is a set of fields that has all the quantum numbers of the proton. So by putting this operator down, you know you're going to excite the proton. But you're going to excite all the excited states of the proton. If you attempted to get information out of this number, that would not make sense. So it would, I don't know if I call it model dependence, but that's some mapping, or not mapping, it's some overlap between your operator should not do is try to extract information out of this object. So in this case, the 3-point function, you have this at the source, at the sink, so you can divide by these functions. The 2-point function, which is exactly the same except it doesn't have this internal current, and then you'll exactly cancel this off to make sure you're not introducing any error into your calculation. So I think maybe not your question, related to your question, people ask questions like, is this state a molecular state or a bound state? So those are questions that maybe are sort of interesting to ask, but they're not well defined, especially in QCD. QCD is just this non-perturbative theory, and what you could find is, for example, the X, what's the number, 387, I can remember. There's been a lot of excitement about this potential DD bar molecular state. What you can answer with lattice QCD is what interpolating fields have the biggest overlap of that state. And you can get some kind of qualitative intuition that maybe it does kind of look like a DD bar molecule as opposed to some deeply bound state. But in a rigorous sense, that's not really a well-defined question. We just like to ask questions like that because it makes sense for quantum mechanics and it makes sense for classical physics. But especially when you get to this very non-perturbative field theory, defining a wave function is not a well-defined question. So wave functions really only make sense in the non-relativistic limit with degrees of freedom that are weakly interactive.
Over time. I saw that the talk ended 3:30. Now I just checked the schedule.
Yeah.
It's 3:15. Sorry. Now, so let's come back at 3:50. It's okay. It's 15 minutes for the dessert. Yeah. Okay. Yeah. So let's thank the speaker again.